Welcome to part 2 of our introduction to Malloc. In this lecture, we're going to be just talking about Malloc and arrays. Not that you necessarily need to know that for the lab, but it is important as we'll use it for later topics in the semester. This lecture will just cover using arrays, Malloc and arrays. The third part for this week then, we'll talk about Malloc and structures. And so both of these last two lectures I'll try to keep short. I say that a lot and I'm not doing it, but I will try really hard to keep this one a little bit shorter. So just as a review, okay, we've talked about Malloc, and then the first lecture we talked about how we can use Malloc to allocate enough memory for simple primitive data types, primitive variables. That is an integer variable or a char or a double or a float or anything. The format, and I still don't think my pen is working. Oh, there it is. All right, so the format then is we're going to have all of our calls, because Malloc, remember, keep in mind that Malloc returns a memory address. It returns a pointer. Its return type is a pointer. It's the void pointer. And so when we return the return value from Malloc, since it is a memory address, we have to store that in a pointer. Okay, so all the variables that we work with when we use Malloc will be pointers. In this case, if I want to declare a simple pointer to an integer, a single integer value, then I would say that this is going to be an integer pointer. I'll call that variable p. Here's my call to Malloc. Okay, we'll use size of and then int. Okay, size of returns the number of bytes that the system will need in order to store an integer type. Okay, we know that's 4 bytes on our Ubuntu systems. And then this portion is the typecast. Malloc returns the void pointer. The void pointer doesn't have a type. It's an untyped object. And so if we don't have to do this, but again, I think it's best practice. And so we want to tell Malloc that you've returned a void pointer, but I'm going to use that memory to store an integer value in. So I'm going to typecast it to an integer value. This piece then, this typecast, when we're doing it using Malloc, can be the same as this right here. Okay. If you forget the asterisk, you're going to have problems. It's not going to be the same. You're going to get a warning or an error. So you need to include that asterisk. It's not the same thing. The asterisk means that this memory is going to be for an integer pointer. We are declaring and using an integer pointer. All right. So that's how that works. Now, this is all simple or primitive, I guess I should say. So Malloc, we're getting 4 bytes here. Well, how do we declare arrays then? And it's actually pretty straightforward. Here's some sample code in the slide deck. It's not actually the same code that we're going to look at in the sample code here, but it's just an example. And go back and think about arrays. And when we talk about arrays, when we introed arrays in 150 and at the beginning of the semester as well, you say that an array in C is going to be typed. You're going to say that it's an int array or char array or a double array. So that means that every single element is of that type, right? If we have a 10-element array, it's kind of like having 10 integer variables. And so we can use that knowledge then to figure out how many bytes we need to allocate if we want to use Malloc for an array. And it's actually pretty simple. So let's say we want a 10-element integer array. Okay, we know that integers are 4 bytes. If we need 10 elements, then we need 4 bytes. We take the number of elements we want times the number of bytes that we need to store those, and we multiply it. And that's all the sample code is doing here. Okay, here I've declared, well, this is dynamic. Okay, so I could declare array size here. I set it equal to 0. I then use a scanf. Okay, and I'm not sure if you guys covered this in 150, but this came up a little bit, and that we would use, when we talked about arrays, we want to maybe dynamically allocate an array using scanf. And this is actually how you would do that. So what we're doing is I'm saying, okay, enter the size of the array here, and then using that integer array size variable, store, using a scanf call, so store whatever the user typed in. Okay, so presumably they would enter in some sort of an integer variable. From there then, and let's just say at this point that they entered in a value of 10. Right? So we ran this program and I typed in 10. So now, if 10 is in the array size variable, I'm taking 10 times 4. That equals 40 bytes. Right? We know that one integer variable so right here, is 4 bytes. And if I have a 10 element array, then I'm essentially saying I need 10 integer variables, 4 bytes in a variable, 4 bytes an element times 10, that's 40 bytes. Okay, so that's how we figure this out. Once we do that, now this is our array, it's a pointer, and we can treat it. We can still use the same exact notation that we have with our other arrays. Okay, we can still use the subscript and access the index. So even though we've declared it using malloc, and this right here is a little bit different. Once we've declared it, we can treat it like we did using the other way, when we would say, you know, int array brackets and however we wanted to initialize that array. Remember that arrays are contiguous blocks of memory. All right, so even with malloc, what this is going to return is 40 bytes of contiguous memory. All right, so let's look at the code. Let's look at some code. There we go. All right, so this is the structures and malloc file, and this is where I jumped around just a little bit in the previous lecture. So what I'm going to do is, now that we've looked at this code, I'll comment that out, and we'll go back to the very top of the program. And you can see here are two samples of declaring arrays. Okay, so just like the sample code we looked at in the slide deck, we're going to say, here's our pointer. I'm going to call this a pointer. So here's our pointer variable. The type is going to be, an integer pointer. Here's our malloc call. Here's our size of call. And then we multiply that by 10. So what this is saying is that I want 40 bytes. I want the size of an int. On this system, it happens to be 4 bytes, and I'm going to multiply that by 10. So that's what's giving me a 10 element array. And again, then I go ahead and I typecast that. And now that we have a pointer, I'm going to move this up as well. We can treat it just like an array. Okay, so after a malloc call, before we do anything, we want to check that pointer does not have a null value. In this case, again, I've not had it happen to me, at least not any time in the recent past. I can't remember any time I've had trouble with it, but it's always a good practice to do that. And let's comment this code out. Okay, this was the stuff that we looked at in the last lecture, as far as declaring just simple primitive types using pointers and malloc, as well as the free. Okay, so keep in mind, remember that after you've malloced memory before your program ends, you want to free it. Once you've freed memory on a pointer, you can't use that pointer again. You have to remalloc memory. But let's go back to, let's talk about there we go. I'll my comment go the other way. All right, and let's look at this code. Actually, boy, I apologize for the mess this is in. I just got things all over the place, and it was in my mind when I laid it out. It made sense, and now that I'm actually talking about it, it's not flowing as smooth as I'd hoped. So hopefully this isn't. I'm not confusing you as I reorganize this a little bit. So to just start over and get everybody back on the same page here, what I did was we declared, using malloc, we declared an integer array of 10 elements. I checked to make sure that our a pointer variable does not contain a null value. If it does, in this case, I just exit the program. Okay, we're in main. If we return out of main, then we're done. The program is done. After we've declared that array, well, we can iterate over it like any other array. Okay, so if I want to, in this case, here is a simple for loop. It's going to loop 10 over 10 elements. I'm going to print the memory address and then the value in that element holds. Okay, a pointer. Okay, so that's a pointer. Right? I didn't declare that the normal way we declare arrays, but it doesn't matter. You can still use the subscript, the square brackets with I, and access those individual elements and do something with them. So in this case, if we run this program, let's see what we get. There you go. There's our memory addresses, and there's the value. Okay, these are hex numbers, and part of the reason why I introduced that early on is because I knew we'd come back and we would use those when we started talking about malloc and pointers as well. I mean, it's important with pointers because that's what we're assigning to our pointers. Hex numbers, okay, so that's a base 16. So once we go past 9, then we start with A, B, C, D, E, F. And so it looks a little confusing, but just remember, instead of counting to 10, you're counting to 16 using those letters. So what does that mean? Well, 8, 9, A, B, C. Those are the 4 bytes that we have to go to the next memory address. And so you're seeing that process repeat: 0, 4, 8, C, 0, 4, 8, C. You're seeing that here's our 10-element array. Each element has 4 bytes allocated to it, and so each address increments in 4-byte jumps. Okay, this is one of the reasons why early on we talk about arrays being a contiguous block of memory. Well, this is what it means, is that each element is 4 bytes, and then the next element is that 4 bytes preceding it, right? So it goes in order. There's something a little misleading about this program right now, and it's part of that unpredictability of a C program. One thing that you may or may not have noticed at this point is that I have not initialized any of the values of those elements. And if you look at the output from that program, they all happen to be 0. And I can tell you that they just happen to be 0. We've allocated memory. We've used malloc to allocate memory for this array, just like we do when we normally allocate an array or declare an array. The fact that in those memory addresses a value of 0 is present, it just happens to be that. That's not always going to be the case. And so just because you're seeing all 0s in my sample program here doesn't mean that there's always going to be all 0s. And so what that means is that when you use malloc, at least I don't know of a better way to initialize all those values to 0. So you may have to, in a loop, do something like this and just ensure that in fact those elements are initialized to 0 so that you don't get any unexpected behavior or unexpected results in your program. All right, let's see here. So that's an array. If you go back up to the top of the program, then you can see here that I declare an array of chars, and it's the same thing. What's the size of a char? Well, at least on Ubuntu, it's going to be, well, I'm in a Windows system, I guess, but it typically is going to be 1 byte. If I want to declare a char array with 80 elements, then I would take that times 80, right? 1 byte times 80, that's 80 bytes. And that's how we're figuring that out. So now, at this point, you know how to do arrays of any type, and you know how to do primitives of any type using this format. Okay, typecast, malloc, and sizeof. And that's what this commented out code right here is. It's the same thing I just did. Just more pointers, more types, and any size that we want. So actually, I'm just going to get rid of that. No, I'll leave it. All right. Going back to this. Okay, last thing I did was I freed that dynamically allocated memory. And that's just the best practice. If you don't free it when the program terminates, I forget exactly what happens, but it can cause issues in the system. And so you want to make sure that you free that memory once you're done with it. Not before you're done with it, but once you're done with it. All right, so what is free? Let's look at I want to give you an example of when we talk about free. Okay, when I talk about free, and using free, I say you can only use it on dynamically allocated memory. Here is an example of a variable. I called it not malloc. I'm pretty sure that's not the way to spell it, but you get the idea. It's not, this variable's been declared. The program, when the program runs, memory is going to be allocated for it right away. It's a primitive type. It's going to be 1 integer variable, so it's going to get 4 bytes. And in this case, I assign it a value of 99. This was not malloc. This was not dynamically allocated. The memory for this variable was not dynamically allocated, so I cannot free that. If I try to compile that program, what you'll see is an error. Oh, actually, it's just a warning. Okay, and so all of this is telling you, passing argument 1 of free makes pointer from integer without a cast. Okay, it's all it's telling you is that this is not a pointer. Okay, free expects a memory address, and this is not what it's expecting. So that's what you get. That's what I'm talking about when I say you cannot free non-dynamically allocated memory. Okay, there's a slightly better way than to dynamically allocate memory for an array outside of using malloc, and that's called a function called calloc. Scroll down to it again, and we'll take a look at, here again is the function prototype. You can see it's very similar. Okay, it's calloc. It's going to be a return type of the void pointer, but we have two arguments for this one. The second argument is the same. Okay, so we're still telling the calloc function how many bytes we want to allocate. The first function, or the first argument, sorry, is a little bit different. And with this one, we're saying how many elements of the array we want. So what does this function do? It requests memory and returns a pointer to it. The difference in malloc and calloc is that malloc does not set the memory to 0, whereas calloc sets allocated memory to 0. Okay, so number of items and the size. Otherwise, everything is exactly the same. So when we look at using that in our program, then, in a program, this is all the difference we would have. Okay, I declared a variable here. I'm not sure why I did that now, but it's an array size variable name, and it has a value of 10. And here I'm using calloc. Okay, just like malloc, except there's two arguments. The first argument is, what is the size of my array? Well, I'm going to declare a 10-element integer array. And then the second is the number of bytes I need. So that doesn't change. If I want a 10-element integer array, then I need to take 10 times the size of int. And that's what we're doing here. What this does then, this ensures that each element has a value initialized to 0. So when we use malloc in that program, when we looked at that array, we iterated over every single element. The fact that it was printing off zeros as the value was we just got lucky. That's not always going to be the case. When we use calloc, that will ensure that those elements have a value of 0. So I can comment this out, and what you'll see is essentially the same thing. Okay, and then I'm going to make sure that I free array pointer when I'm done. Okay, so same thing that we did with the last array. I'm going to print out the memory address, and I'm going to print out the value. And you'll see that there's no appreciable difference here. Okay, what was my error? Redeclaration of I with no linkage. Okay, so what does that mean? That sounds kind of complicated, but all it means is that I've declared a variable size underscore ti here, and then I tried to redeclare it here. Since I already have it declared, I just need to get rid of this. Okay, I'm using it in a for loop, so the for loop will initialize that I variable to 0, so I don't have to worry about it. Okay, now I compile without any errors or warnings, and if I run the program, okay, we have two outputs. One, this first one we can ignore because we've already looked at it, and that's the array that we declared previously. The second one is the array that we declared using calloc. So this is with malloc, this is with calloc, and right now you can't see a difference, right? The only thing is, the big difference is, these I know are zeros. I can guarantee these are set to 0, and these values right here, I'm not sure if they'll be 0 or not until I actually initialize them myself, which I guess I did. If you go back and look at the code, I did make sure that those are zeros. So if I take that out, and we just compile this again, okay, doesn't generate any errors or any warnings. We can run this multiple times, and you'll see those values are pretty much always going to be 0, at least when I'm running it, but that's not a guarantee. Okay, this is not a guarantee. This is malloc, calloc. Okay, that's arrays. Okay, so you can use malloc, you can use calloc. I recommend calloc when you're working with arrays. If you want to use malloc, just remember that you can't guarantee that those elements are going to have a value initialized to 0. So if you don't do that yourself, or the first thing you do with them is set their value to something you control, you could get unexpected behavior in your program. The last thing I want to do, and this is kind of an aside, Okay, I just wanted to point this out. Hopefully it helps better understand memory addresses and pointers, but maybe not. It might be more confusing. So we're not going to do any of this. I will never ask you anything about this on a quiz or an exam, or won't be in anything in the lab, but it is just something I want to spend a few minutes and talk through. And that's called pointer arithmetic. So if we go back to the size of program, and I'm going to just comment out this one printf so that I can limit some of the output. If we go back to the size of program and we look at this sample code, what we can do then is there are limited situations or circumstances where we can do something called pointer arithmetic. And that is that we can actually manipulate our pointers by doing some mathematical expression on them. For this program, we have an array 1. Okay, it's a 5-element array, and I've initialized the values to 1, 2, 3, 4, 5. Okay, this is the old school way of doing it. This is the way that we originally learned. The second way is, well, I just declared a pointer. And this pointer is going to point to an integer type, and I'm going to initialize it with the value of our array 1. I could also have just done this and provided it the value of the array 1 variable. But either way, it doesn't matter. What I want is the memory address to the first element in this array, array 1. Remember that when we declare an array, this declares, it gets the memory in contiguous blocks. Okay, so now when we use malloc, when we go back and we look at that, we can see that when we use malloc to declare an array, we get 4-byte blocks of memory contiguously, right? So if it was, the memory address was, 0000, then the next one would be 0004, then 0008, and 000C, and so on. It would repeat. They would be contiguous. So we can guarantee jumping in 4 bytes at a time that we would be within our array. So we can manipulate the pointer itself to move around those memory addresses. So let's take a loop here, and we'll initialize I to 0, I is less than 5, I plus plus. Okay, so standard loop to iterate over every single element of an array. What we're doing then in the printf is we're not using, well, I'm going to print off the memory address and the value. But what I'm doing is I'm not using the same notation. I'm not using the square brackets with the index. I'm not using I at all to do anything, to interact with the array. I'm only using it to control the loop. So what is a pointer? A pointer is a variable. Its initial value is the memory address for the first element of the array. So I'm going to print off the value of that pointer, and then I'm going to dereference that pointer and print off the value that it points to. So what we should see is the values 1, 2, 3, 4, 5, and those 5 contiguous memory addresses that have been allocated for it. Okay. Keep in mind, this is not dynamically allocated. Memory is going to be allocated for this array once the program runs. How I iterate over the entire array, though, this is where the pointer arithmetic comes into. Okay, so if I do a pointer plus plus, then this is going to iterate over each element of the array. So let's go ahead and run this program and see what happens. Conflicting type. So what did I do? Probably, yes. Okay, so I declared array 1 already in this program when I was doing some ad hoc examples. So I want to get rid of that, and hopefully that gets rid of my error. Nope. Yep, same thing with a pointer. Okay, so I have a pointer here, and I have declared it right here as well. So probably the easiest thing to do is just to do a bulk comment. Okay. And I will go back. All right, that takes care of all of that. Now we'll run this program, and there's our output. Okay, so we know we iterated over the array because we printed off the values 1, 2, 3, 4, 5. Those are the values in the 5 elements of this array. The next thing we did, as you can see by printing off the memory address, that we jumped or moved in 4-byte increments, right? So 24, 28, 2C, 30, 34, and we could continue on. All right, so that's pointer arithmetic. So how does it work? How did this actually result in us moving 4 bytes at a time? Well, you need to keep in mind that when we do plus plus, what we're doing is we're taking the number times its byte value. Okay, a pointer is this pointer right here is pointing to an integer type. So if we do the increment operator is like adding 1. If we add 1, we multiply that by its byte value. The byte value of an int is 4. It's like saying a pointer plus equals 4. Okay, so reserve the 4 place. So a pointer is the same as saying a pointer plus equals 1 times 4. That's what we're doing, and that's how we move in 4 bytes at a time. That's how we hit every single element of the array. What happens if I do this? Okay, so let's take out our a pointer increment. Let's say I do a pointer plus equals 2. This is wrong, actually. More like that. You know, I'm not sure if that even works. Let's just get rid of it. All right, so what happens if I do this? A pointer plus equals 2. Run the code, compile it, run it, and look what happened. Okay, 24, 2C, 34, 3C, 44. Okay, so we moved in 8 bytes. So we took, instead of taking 1 times 4, we took 2 times 4. So we moved in 8-byte increments instead of 4-byte increments. This is an integer array, so we wanted to move, well, if we want to iterate over every single element, we want to move 4 bytes at a time. But in this case, we moved 8 bytes. So that's why we print, it's like essentially skipping every other element. So we printed off the first one, we printed off the third one, and we printed off the last one. What happened here, though? Well, this is part of that unexpected nature of memory addresses and pointers. Okay, this didn't generate a seg fault. It very well could have, but it didn't. But what happened is, though, we were jumping in 8-byte increments, and our loop was set up to do 5 iterations regardless. And so once we hit that last element, we jumped into memory that has not been allocated to us. So this address here and this address here, this value, for all I know, that's a value, that's a memory address, a location that's being used in another program that's running right now on my system. I don't know what it is. We don't know what it is. All we do know is that I shouldn't be trying to access these values, right? So if you decide to use pointers and iterate over, and the same thing with when we just use arrays, okay? So when you iterate over an array, that's why it's important to make sure that you don't iterate past the length of the array. If you have a 10-element array, you iterate 10 times, no more than those 10 iterations. Well, no more than you don't go off the end of the array. You don't go beyond the number of elements that are available, because this is actually what happens. You start using memory addresses in memory, and you may have used this value. Maybe you went off the end of the array and you used that value to calculate the average, and your average is way off. Well, this may be why. You go too far, and you'll eventually crash your program, segmentation fault, because something unexpected happened. So this is why you have to be very careful when using arrays in C, that you don't iterate off of the end, because it's very easy to do, and you notice that when I compiled this program, it didn't tell me anything was wrong. It just went ahead and let me do it and run it. In this case, it just happened to work. And see, I'm getting the same value every single time. So odds are, whatever used those memory addresses, those locations, it's not using it anymore. It's been deallocated, and it's just sitting there. It just needs to be allocated to something else. Yeah. All right, I think you get the point. So then we could continue on. If I wanted to say pointer plus equals 4, what would happen there? Well, we'd take 4 times 4, and we'd do 16-byte increments, right? So we'd, well, I don't know, we'd hit 1 element, and that would be about it. And then the rest of it would be off into memory that has not been allocated for our program. So we'll compile that one more time, and then we'll run the program. Okay, see, so I guess we have 2. So 1 and 5, and now we have 3 values that aren't necessarily ours. And we get the same thing over and over again. It's not generating a seg fault, but it very well could. All right, so that's pointer arithmetic. Again, the point hopefully it wasn't to confuse you. It certainly wasn't that. Hopefully it helps understand further how we're working with memory addresses, how we're allocating memory. One thing to keep in mind: this only works with array elements. This only works with when you're using pointer arithmetic. Don't want to use it in anything else, because arrays are the only thing that we have contiguous blocks of memory for. So it's of limited value, but it does give us some insight into how that memory is allocated for, at least for an array. When we look at structures, those are going to have memory allocated for it. and that is not going to be contiguous. Okay, so it only works with arrays because arrays give us a contiguous block, continuous series of memory addresses. Let me just make sure I didn't miss anything. Go through this code. Okay, there's our calloc code. Let's see here. Yeah, so we could look at this. We've already done it, so I won't spend any time on it. I'll just uncomment it so you can see it. And this is just using pointer arithmetic. Right? So if you wanted to go through and use pointer arithmetic for an array, that's fine. I don't expect to see it in anybody's code, so don't feel like you have to. Again, just use it to talk about memory allocation and memory addresses. So that's all what this code is for. The last thing I want to point out, and this is just hopefully to prevent anybody from running into any issues with it, is let's look at this test array function. Oh, see, I'm doing it again. It's going to be another long lecture. Let's look at that test array function. And it's a very simple function. Its return type is void, and it has one argument, and that is an integer array. So nothing new there. We've done that in plenty of code. If we go down, let's see, scroll all the way down, what you're going to see inside the function is all it does is it prints off the size of a. What is a? Well, a is our argument, the variable name of our argument. So what it prints off then, oh goodness, you know what, I forgot to show you guys something here. Let's see, how did I miss that? All right, so before we can do that, I forgot to show you guys something, so I apologize. Let's take a look at that real quick. Let's say that we want to printf and the size of the array, and we'll do %li at the new line, and I'll call size of on array 1. Okay. I'm going to go back into this code, and I'm going to make sure that I at least comment out the printfs in these loops, because we don't want any more output in the terminal than we need to look at right now. Okay, let's go back to the code. Let's see if that'll compile for us. Oh, yep, okay, I got a straggler for my comments. Obviously, that line highlighted in bright pink was the culprit. Okay, so we clear that up, and now we run the program. Ooh, aborted core element. All right, so something bad happened. Let's go back up here, and because I don't want to waste your guys' time watching me troubleshoot, I'm just going to bulk comment things out. Let's see if that got it. Okay, good, that got it. So I had an error somewhere in that pointer arithmetic code that I just uncommented. So I'll fix that before I upload the code. What did we get here? So okay, so the output of the program was the size of the array is 20. And if we go back and look at array 1, what do we have? We have 5 elements, 1, 2, 3, 4, 5. We know that they're an integer type, so 5 elements, 4 bytes per element, 20 elements. So when I called the size of on array 1, that gave me 20. That says that the size of that array is consuming or holding or occupying 20 bytes, right? 20 bytes, again, regardless of what I actually store in here. If I commented out 3, 4, and 5, or got rid of them, right, it's still, well, in that case, it is a 5-element array. Let's say I added this, okay? I'm still declaring a 5-element array, even if I only initialize 2 of the elements' values to something other than 0, it's still going to be 20 bytes. Now, if we look at the test array function, what we're looking at is essentially doing the same thing. I'm going to print off the size of and then the argument, or the variable for that array. So if we go back down here and we look at, okay, here's the array, here's A, and I'm just printing off the size of A. Well, you already saw the output, and what was it? Well, it was 4, right? Because a pointer, an integer pointer, it needs enough memory allocated for an integer. So it's going to have 4 bytes. That's where it's going to store. That's what it's going to point to. It's going to point to an integer type. An integer type means 4 bytes. So when you use it, size of, in a function, and that function is that argument is an integer type, you don't get the same result. Okay, so that's the only reason I wanted to go through that, is just a caveat or to warn that using it in this context with the variable itself as a non-argument, you get what you were expecting. You're getting the size of the array 1. It's holding 20 bytes. But in the function, you're not. You're getting how much that is pointing to, which is 4 bytes. Okay, so just keep that in mind. Okay, that's it. Apologize for the lecture going a little bit long, and there'll be the third part, and we'll talk about malloc and structures.